Hi guys, welcome back to the channel. In this video we are going to discuss mod-5 up counter and mod-5 down counter. So let's get started. So these are the things that we are discussing up to now in the previous videos, that is full modulus counters. So what is meant by full modulus counters? So it is nothing but the general thing, the normal modulus things that we are going to see. So if you see the first 2-bit counter that can have the modulus 4, means it can count up to 4 mod states. So it cannot have in between states, means with the help of that we cannot calculate mod 3 counter, means we cannot calculate, or we cannot count 3 states, we cannot count 2 states like that. So if you see the second one, that is mod 8 counter, it can basically start at 0 and end at 7, and vice versa. It can start at 7 and it can end at 0, but it cannot have mod 5, means it cannot count mod states. So like that it cannot go up to mod 5, and again it cannot go to 0, like that it cannot go to as reverse. So this is the basic thing of mod 8 counter. These are full modulus, means up to 2 power n I can say. So the next one is mod 16 down counter. So like that you are having the only full modulus counters. But in this video we are going to cover the mod 5. So let's see how to do that. So this is the thing that I am saying about. So the first one is starting at 0, ending at 3, and again going to 0. So the next one is starting at 0, ending at 7, again going to 0. So the next one is starting at 0, ending at 15, and again going to 0. So like this is mod 16, mod 8, mod 4 counters. So for the mod 5 counter, the first step is to identify the number of flip-flops. So because this is the very important step, so we can have the mod 5 counter with the help of this first one and the second one. So if you observe the first one, we are going to count the 5 states. So starting from 0 and ending at 0. Total states is 5. So 0, 1, 2, 3, 4, 5. That are total 5 states. So using the 4 flip-flops also we can construct from starting from 0 and end at 4. But it is very important. Ultimately we are going to use the small number of flip-flops to build the mod 5 counter. So we can use the both of them, but we are going to use in this video the using 3 flip-flops. So let's start with the first, means 3 flip-flop things. So we now understood how many flip-flops it requires. So we total require 3 flip-flops to construct the mod 5 counter. And we need to understand another point, that is it will start counting from 0 and end at 4. Because total 5 states it will be going to count. So that is known as mod 5 counter. So 0, 1, 2, 3, 4, and again 0, 1, 2, 3, 4, like that it will count. Now it is very important to understand, as we are using 3 flip-flops, according to 3 flip-flops total, according to normal rules, if you construct with the normal 3 flip-flops, we are going to have total 8 mod counter, means it will count up to 8 starting from 0 to 7. Then how we can break at 5th position? So if you can observe, we are going to start at 0 and end at 4. While if you see 5, you are going to break the circuit, or we are going to break the chain, and we are going to again go into 0. So the breaking point is 5. So now at 5th position we are going to do something to 5, so that it again going to 5. So that is the main aim of our goal. So the 5 we are going to take out, and we are going to have some logic in the 5, and we are going to have our output again to 0. So the 5 is the output 5 is, that is 1, 0, 1. So not only that, now if you want mod 6 counter, you are going to start at 6. So that is the thing. So the main logic is how many states or how many things that you want. So the next step you are going to have some logic. So the logic I will going to say in this video. So as you are going to have the mod 5, so you are going to have the 5th position, that is 1, 0, 1, that is Q0, Q1, Q2 positions. So at the 5th position, all the things, all the flip-flops will be resetted to 0. So that is our main aim, right? So for that purpose, we are going to use the NAND gate. Why we are using NAND gate? Because if you pass the 1, 1, 1 into the NAND gate, the whole output would become 0. Because 1 into 1 into 1 whole bar is 0. So that is the situation. So if you observe the 2 input NAND gate also, when you pass 1, 1, the whole output would be 0. So this is the NAND gate that we are going to use in the flip-flops for the mod 5 counter. So let's see how to use these NAND gates. First of all, we need to construct the mod 5 up counter. Mod 5 up counter. For that, I am taking the mod 8 up counter. Mod 8 up counter. First of all, we need to take the majority of the thing, means the full modulus counter. In the full modulus counter, we are going to have some logic, so that we are going to obtain the mod 5 up counter. So I took the mod 8 up counter. We are going to have the NAND logic now. So remember this thing, we are going to have the clear input signals also. That is very important thing. So clear means we have already discussed in the previous video. We have separate video that is clear and preset for that. So check out that video. I am giving that video in the description box. So it is nothing but it will clear all the things. So whatever may be the outputs, then that if you pass clear as 0, whole outputs instantaneously it becomes 0. So that is the main use of clear. Now we are going to have the main logic for the mod 5 up counter. So Q0, Q1, Q2 is 101 now. So we are going to have all clear as 0. So for the 0 in the NAND gate we are going to have 111. So as we have to connect all the outputs Q0, Q1, Q2 to the NAND gate, because this is the 3 input NAND gate. So if you observe the first input is 1, so that is okay. Means if all inputs are 1 only, the whole output would be of 0 will be for the NAND gate. So the first input from Q0 is 1, so that is okay. So if you see the second one, that is Q1, we are passing 5, right? So that is 0 indicated with 0. So we don't need as input for the NAND gate as 0. So we are going to invert that with the help of NOT gate, and we are going to take in the NAND gate input. So the third one is again 1. So that is again we required 1 only. So pass all the 3 inputs at a time, we are going to have 0. So when you reach the fifth position, we are going to have the NAND gate output as 0, and it will clear whole outputs. So again we are going to start at 0. So this is the logic with the help of NAND gate. Mod 5 up counter has another representation also, that if you not represented the Q1 also, it doesn't make any sense because both the circuits are same. So in this we are going to use the 2 input NAND gate and connect Q0 and Q2 to the NAND gate. So whenever it see both of the inputs 1 means the Q0 and Q2 as 1 1, the whole output of the NAND gate will be 0, and it will pass whole to the clear and it will be cleared. So basically again it will be going to 0. If you see the 1 0 1, so if you know don't pass Q1 also, it doesn't make sense. So now let us understand how it doesn't make any sense without passing the Q1 also. So if you clearly observe the truth table of the outputs, that is Q0, Q1, Q2, we are going to have some logic at 5, right? So in the fifth position we are going to have 1 0 1. So don't consider Q1 because that is 0. We are only having Q0 and Q2 connecting to the NAND gate. So if you read the statement that the first time it sees the Q0 and Q2 as 1, then it will be reset because we only connected Q0 and Q2 to the NAND gates. So what is this statement means? So if you see in the truth table, we doesn't have any other remaining possible cases where the Q0 and Q1 as 1 1 up to it is reaching fifth position. So after it sees both the inputs as 1 1, then it whole output becomes 0. So we already know about NAND gate. When both of the inputs are 1 only, the whole output becomes 0. Otherwise when single one of the input is 0, the whole output again becomes 1. So that is the case. When fifth position only, the Q0 and Q2 becomes 1 1. So that is the scenario here. So that is the reason without using the Q1 also the whole work is done. Now we are going to understand the mod 5 down counter. So for the mod 5 down counter also, first of all we need to have the mod 8 down counter. The big one we are going to have some logic so that we are going to obtain our required thing. So I took mod 8 down counter first. So as it is the mod 8 down counter, so what is meant by that? It will be going to start from 7 and end at 0. Again it will be going to start at 7 and end at 0. So this sequence will be continuing, and you can also observe in the truth tables as well. Now we are going to make some changes in the 3-bit counter to get the down counter sequence, that is 76543, because as this is the mod 5 down counter, mod 5 this is, so this will only calculate 5 states. So starting from 7, this is the down counter, we took the down counter itself. So starting from 76543, so these are the total 7 means the 7 minus 3 is 5. So we are going to have the total 5 states, and in the second state, that is in the second position, we are going to have some logic for the second position, means the second min term. So for that we are going to have apply some logic as we have done in the previous one. So applying in this, we are going to have the logic in the NAND gate, so that we are going to reset our flip flop again to 7. So after crossing 3, if you reaching 2. So there are many ways to represent the mod 5 down counter. First of all, we need to understand with the NAND gate, because we have already saw in the up counter, mod 5 up counter. So in this, if you consider, we are going to connect preset bar. So this is known as active low inputs. Basically, if you pass 0 from the NAND gate, we have a bar over the flip flops. So what the bar do? So 0 will be converted as 1. So we are going to have the preset as 1, then only all the flip flops will be resetted to 1. So our aim is to reset all the flip flops to 1. Whatever may be the outputs currently present at Q0, Q1, Q2, finally we are going to obtain, or we are going to reset all the flip flops to 1 1 1. That is our aim. So the preset bar does that only. It will convert all the things to 1. And the connections I made for 2, you can simply see that is Q0, Q1, Q2 as 0 1 0. So as it sees 0 1 0, that as same pattern, that is Q0, Q1, Q2. So you can also observe that. So we have Q0 as 0. So for that, for the NAND gate input, I took the output as bar, because the NAND gate accepts only the 1 as input, because all the inputs are 1 only, the output becomes 0. So for that purpose, the first one would be Q0 would be, we have to invert that. So second one Q1 we can take directly. The third one we have to invert, because that is Q2 as 0, we have to invert and take that as 1. So with the help of the NAND gate, this is the mod 5 down counter. I hope you can understand this. All the things would be same, but we have a little change over here. We need to apply the preset, not here clear. We should, that's remember, it's very important point. If you So this is the second representation of mod 5 down counter. If you see here, the preset is active high input here, because the AND gate is replaced with the help of the AND gate. But all the bubbles in the flip-flops are removed, because the NAND means not is cancelled, and you can have the simple representation, because each and every flip-flop has NOT gate. So the NOT gate and the bubble for the NAND gate is cancelled, and we can simply represent with the AND gate. So you can have the preset as high only. So if you observe, as this is the AND gate, if you pass all the 3 inputs as 1 only, the whole output would be 1. Then only all the flip-flops will be having the preset as 1 at a time. So remaining all things would be same. For the, when you see the 2, that is Q1 means the Q0, Q1, Q2 as 0, 1, 0, the whole the 3 flip-flops will be. So for the first flip-flop Q0, we are going to send 0. With the help of the NOT gate, we are going to take for the AND gate. So second flip-flop as it is Q1 as 1 only. For the third flip-flop, we are going to pass 0, and we are going to have the NOT gate and 1. The finally 1 into 1 into 1, that gives 1. So this one we are going to directly apply in that. So this is the active high inputs preset. And finally we have another kind of representation. So as you can see clearly, why we need the requirement of the NOT gate. Simply if you are already having the Q0 bar and Q1 bar and Q2 bar, so you can see over there, this is the condition, that is 0, 1, 0. So you are going to take for the first one, that is NOT gate. So instead of taking NOT gate, we just had the Q0 bar. So take Q0 bar directly for the first case Q0. So in the Q2 also we are going to take the NOT gate. So why there is requirement of NOT gate? We have directly Q2 bar as output, direct output, right? So we can take that directly as that from Q2 bar. So if you have the output, that is 0, 1, 0, you are going to take Q0 bar, that is 1, and Q1, that is 1, and Q2 bar, that is 1. So in this situation, we are going to have the AND gate output as 1. So it will pass all the way to 1, and all the outputs means all the outputs becomes 1. Whatever may be the outputs, whole outputs become at the time. So this is also preset active high inputs. I hope you can understand this one. So if you are more much interested in these concepts, so in the upcoming video we are also going to discuss about mod 10 counter. So I hope you understood this video. Thanks for watching up to now.